Let's have a look at solving some linear equations. Here we have x plus 4 equals 8. Splitting the page like this to represent a balance or an equals. On one side of the system, I can put an x tile and 4 1 tiles to create x plus 4. And then on the other side of the system, I'm going to have 8. And I know that these balance because I'm told by the equals sign that x plus 4 is equal to 8. What I want to do is isolate x. And I'll use this language with children. Isolate x, leave x on its own, find x, isolate x. At the moment, x is not isolated. There are other things on the same side of the balance as x, and I want to remove them. The way I'm going to do this, because I know the idea of zero pairs, I'm going to introduce some zero pairing. So by introducing 4 reds onto this side, I know that the balance would become unbalanced, and I need to introduce the same amount on the other side. So this keeps the balance equal, and we know that these are zero pairs, which means they eliminate each other and therefore can be removed. And now we're left with x isolated and x equals 4. Suppose we have this one. 2x plus 1 is equal to 11. So I have 2x plus 1 on one side, and on the other side I'm going to have 11. So 2x plus 1 is equal to 11. And I wish to isolate x. At the moment the x's over here are not on their own. Let's see if I can get rid of this pesky yellow. Introducing a zero pair, I need to do the same to both sides of the balance. These eliminate each other and can therefore be taken away. I want to leave x on its own. At the moment I've got 2 x's, so I wonder if I can create 2 equal groups. Yeah, I've made this one quite an easy question. I can create 2 equal groups. So I know that 1x balances with this and 1x must balance with this. So I can ignore this part of it and leave x is equal to 5. Let's introduce some brackets. The way in which we build this question up is really important. The way in which we tell the story of this. So I have x plus 3. So I've got x plus 3, x plus 3, but I have 2 of those things. So I have 2 of those, 2 lots of x plus 3. And x plus 3 in this case is going to balance with 8. So put 8 on the other side. There are several ways of solving this. I could immediately introduce zero pairs, or I can create 2 groups and do it that way. I'll introduce 0 pairs. So I wish to get rid of all of these yellows over here, which means I've had to introduce 6 things to this side of the balance. Imagine 6 new things weighing down the balance over here, which means that 6 new things have to come to balance that out over on this side. We know that these are all 0 pairs. And now I'm left with 2 x's over here, some material over here. I want x to be left on its own. So creating 2 equal groups, which I can do, I can see that 1x is equal to 1. Let's try another one. This time we've got negative 3, x minus 1 is equal to negative 6. So minus 3, x minus 1 equals minus 6. And now the process of using 0 pairs becomes obvious why I've been doing that rather than taking away yellows. So let's build this up. I've got x minus 1, I've got x minus 1, x minus 1. Well, I've got 3 of those. So I've got 3 lots of that thing, x minus 1. So x minus 1, 3 of them, but I've got the reverse of it, the negative of it. And we've spent time in earlier years discussing that the negative of an algebra tile is what's on the reverse of that algebra tile. So this is my system. And that is going to balance with minus 6. So I've got 6 reds over here. And you can see now why earlier on I didn't just subtract yellows from one side of the balance, because I couldn't do this in this case. Whereas if I'm adding into the system, I can always add into the system. So I want to get rid of these yellows over here to leave x's on their own. I'm going to introduce 3 reds, which means on this side I have to introduce 3 reds, and you can see over here now the children have been doing a directed number and another directed number. These are 0 pairs over here, so they are 0, which means I don't have to have them in the system. And now I have 3 x's over here. Can I create 3 equal groups? Yeah, I can do that. So I've got 3 equal groups. I'm only interested in one of the x's. I want to isolate an x. So I can remove those. This isn't x, this is minus x. I want to have x. So what I have to do is to have the reverse of what I have here. Turning everything over, and x equals 3. What about if we have a situation like this, where we have 2x equals 1? And earlier on we were saying, can we split it into equal groups? And in this case, I can over here. I can split this into equal groups. What about this little thing here? Well, of course, it can be split. It can be split into 2 equal things. It can be split into halves. I'll very often give young children scissors and allow them to cut across the diagonal like this and divide it out into halves so that they can see that this thing's being split into the same number as well. Equally, if this had been a 3x and I'd had 3 on this side over here and that was equal to 1, then the children can split this up into thirds like this. If over here had been equal to 2, then again they can split it into thirds by cutting, distribute these thirds, and I'll have 2 thirds here, 2 thirds here, and 2 thirds here.